Some other features I'd like to talk about on the dyno spec screen is this estimate required inertia. Many times we have people call up and how big a flywheel do I need for a certain size engine? And anyway, we provide this feature up here in the dyno specs, estimate required inertia. And if you click on it, like it says, we don't check all the safety factors. We check just one simple safety factor of what you're doing here, but you've got to design your dyno system to be safe. And one way to make it safe is to keep the RPM low. So you can see here are the testing estimates. Here are what you think your engine is going to be doing. And the first thing here you see, what is the average engine torque the engine's going to be putting out? Now, you probably don't know what that's going to be. You have some idea on horsepower, and you know about where the horsepower peak's going to be, but you don't know how much torque that means. So I'm going to give you the equation here for figuring it out. Torque is equal to horsepower times 52 divided by RPM. So let's say let's say you're going to be testing up to 35 horse engines, and you know they peak around 7,000 RPM. If you go through this formula, it ends up being about 26 foot-pounds of torque. Now, at the horsepower or at the torque peak, you're going to have more torque than at the horsepower peak, maybe 30 foot-pounds, maybe 32. But at other RPMs, below the torque peak, above the horsepower peak, you're going to have less than this torque that you get at the horsepower peak of 26 foot-pounds. So 26 is a reasonable average. The torque you get at the horsepower peak is a reasonable average for the average torque throughout the whole RPM range. So what you would do is we would now type in 26. And let's say you want to start at 3,000 RPM and go to 7,000, or 7,000 is the peak. So you're going to want to go well past that if you feel comfortable doing that. Do not rev an engine past where you feel comfortable revving it. It is better to just accept the data at a little lower RPM than to risk hurting anything on the dyno or yourself. And the desired accel time, I like to see 6 to 10 seconds. I don't think there's much advantage of over 10 seconds. 12 is not bad, but 30 seconds is, you don't want to go for that. You're really wasting time and stuff. But 5 seconds, I would say, is about the minimum accel time. Now, if you go 5 seconds, you'll get by with less inertia. So that's the thing to realize, that if this is your worst case, 35 horse engine is your worst case, and most of them are going to be more like 20. Maybe for this worst case, you'll accept 5 seconds, knowing that for the smaller engines, you'll have more than enough inertia for a good 6 to 10 second accel. But I'm going to pipe in, let's say, 6 seconds for this one. And you can see up here, the required inertia is about 124 pound-foot squared to do this. And you can see here, the wheel RPM at the end of your test at 8,500 RPM is going to be 2250 RPM. Now, I would certainly not like to see that up around 3,000. Around 2,000 seems to be pretty good. I've never heard of anybody report problems. I've never heard anybody report any problems of a flywheel coming apart, except one guy had a hollow shaft, 1.25 inch hollow shaft. He had a problem. So definitely do not use the go-kart shafts that are hollow. But if you wanted to keep that a little bit lower, let's say you want to go to 4-to-1 gear ratio, and that keeps it a little bit lower down to 2,100 RPM. And you can see here we need 139 pound-foot squared of inertia. The current inertia on this screen here, this changed from our last, this was 4 before, 4 inches thick, is about 135 pound-foot squared, which is very close to that, which means that this would be a good setting of 23 by 2.5 inches thick to handle this size engine peaking or revving from 3,000 to 8,500 in 6 seconds. Now, if you want to do something else, there's other combinations up here that will also work. But the important thing to remember, if you go with a 4-to-1 gear reduction with this size engine doing a 6-second accel, the required inertia is about 140 pound-foot squared. So let's get out of this screen. We know that this has to be about 140 pound-foot squared. So let's say I can't make a 23-inch diameter. My lathe will only handle something up to 18 inches. Well, you can see I'm down to 50. How thick do I have to make this thing to get back to that 140? And you can see it has to be 7 inches thick if I can only do an 18-inch OD. This over here being blank or 0 means it's a solid shaft. Now technically you got the shaft going through there, and maybe you got a 2-inch shaft on this thing, but you can see it dropped it almost nothing in weight and nothing in inertia. So the inside diameter is something this is not real critical until you start making thin walls things like rollers for chassis dynos. Then the inside diameter is important. But anyway, 500 pounds, but only 140 pound-foot squared of inertia. So let's say if you go bigger like we had before, 23, or let's go 24. 24 OD by 2.2 inches thick, it's only 280 pounds of steel, and you get the same inertia. So the important thing here is the diameter really helps. Now, if you go too big, let's say, you see how little weight we can use? But you are getting to have such a thin disc here, 35 by ½ inch thick. Do not do this. This is a very unsafe. It's a pancake, and it is not a safe way to build a flywheel. You've got to have some thickness for the diameter you're working with. So I've never seen anybody go less than, I've seen 7/8 of an inch thick. I don't like that. I would say 1 inch by 24 is about as thin as you want to make a 24-inch diameter wheel. This is way, way too thin. So this is how you can estimate the required inertia and what combinations of OD and thickness will give you the required inertia. Now, when you've made all your changes, and let's put this as back. I was playing around here showing you how to estimate the required inertia. Let's say you bought the system and your flywheel set is already set, and it is, those are the settings, I'm sorry, 1.5 inches thick. This is your dyno setting, and you got a 2-inch shaft on the OD, and the shaft is 23 inches long. You got your one-way clutch in here, a little drawing here showing you how everything works out, and you can see this shaft here has no effect at all. And we got 96 pound-foot squared of inertia, and that is your right gear ratio. And we are with a clutch. We're going to measure engine RPM. And this coast down data, if you don't have coast down data, blank this out. You do not want to fake this because you can really screw things up. So if you haven't done a coast down test yet, you want to blank this out. Want to blank it out like that, and a little screen here that here you can calculate based on number of teeth and stuff your gear ratio. And let's say on the engine side you got 22 teeth, and on the dyno side you got 91 teeth. That's a 4.14, and if that's what you had, 4.14 is what you got. Now from all these changes, you want to save them. You can save them with this test up here, but the more important thing to do, and the program would not let you screw up too much here, but you want to save them as the master dyno specs. And we'll get into this a little bit more later. The master dyno specs are what's going to be used every time you do a new test. And like I said, I'll get into that, but you want to save them as the master. You're back out of this screen, and you're back at the main screen. And these numbers here probably have changed because we changed the dyno settings. But that concludes our dyno specs.